Lesson 11.2, Simplify Radical Expressions. You should be on page 719. A radical expression is in simplest form if the following conditions are true. The first condition, there are no perfect square factors other than 1 in the radicand. Now remember, the radicand is the square root symbol, so the only numbers underneath here can be non-perfect squares other than 1. If I have a perfect square underneath, I should take the square root of it, is what that's saying. There are no fractions in the radicand, so I can't have any fractions inside a radical. And no radicals can appear in the denominator of a fraction. These I would definitely get in my notes. These are the 3 steps to having a radical in simplest form. Now there's a key property we're going to have to use in order, actually 2 key properties. Here's the first. This is the first that will help us accomplish these 3 things. It's called the product property of radicals. And what it says is the square root of a product equals the product of the square roots of the factors. Now you might be like, that's confusing. Okay, it's a pretty simple property. What it says is if you have a radical, you can take those factors and break them into separate radicals like you see here. Here would be another example, like the square root of 4x. I could break that into the square root of 4 times the square root of x, and think about it. What is the square root of 4? Well, that's 2. So the square root of 4 times the square root of x would actually end up equaling 2 times the square root of x. That's the product property of radicals. Here would be another simple example of that, like the square root of 45. I could break that into square root of 9 times the square root of 5, and since the square root of 9 is a perfect square, that would be 3 square root of 5. I just used the product property of radicals. You can also use the fact that the square root of a variable to the second power equals that variable, where that variable is greater than or equal to 0, to simplify radical expressions. In this lesson, whenever a variable appears in the radicand, you always assume that it only has non-negative values. So these variables would always be considered positive amounts for these problems. Okay? One thing I have to, let me erase this so you can read this. One thing I need to remind you of is you need to know your perfect squares in order to get this done. Now let's review our perfect squares real quick. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and so on. We need to know our perfect squares. That takes us back to chapter 2. Here we are again. Have to remember these. Okay? Because when you are trying to simplify a radical, you have to know the perfect squares. Here would be a couple example problems, like here. The square root of 32. When you break this up, you want to try to break it up into a perfect square times something. So ask, what perfect square, which of these numbers divides into 32? Well, there's a few of them. 4 does, 4 times 8, but so does 16 times 2. Always pick the largest perfect square. So the square root of 32 would be the same as the square root of 16 times the square root of 2, and the square root of 16 is 4, so you end up with 4 square root of 2. Now all these rules here were accomplished. We have no perfect squares underneath the radical anymore. That's what this first thing says. We don't have any fractions in here, and we don't have any radicals in the denominator. So all 3 of these rules were covered here. We simplified the radical. Here's another one. The square root of 9 times x to the 3rd power. Well, let's break that up into the square root of 9 times the square root of x squared times the square root of x. Now, here's my x to the 3rd power right here. I have 1, 2, 3 factors of x. I just wrote them under different square roots. Here's why. What is the square root of 9? It's 3. What is the square root of x squared? Well, we just from here. It's x, and then this square root is trapped. I can't get that x out of there, so 3x times the square root of x, I just simplified that radical. why don't you pause the video and try these two? And I'm back, and for the square root of 24, what perfect square on this list divides into 24? Well, 4 does. 4 times 6 is 24, and the square root of 4 is 2. So I just simplified the square root of 24 into 2 radical 6. Now, 6 is not a perfect square, so it did follow that first rule of no perfect squares left in a radical. And then the square root of 25x squared, I could break that up into the square root of 25 and the square root of x squared. The square root of 25 is 5, and the square root of x squared is x. I just simplified that into 5x. Let's talk about multiplying radicals. Sometimes it's nice to be able to multiply our radicals together because they simplify easy. So look at this example. The square root of 6 times the square root of 6. Well, I can put those underneath the same radical, which would give me the square root of 36, which gives me 6. So this is taking me back to the product property of radicals. I can take factors and break them into separate radicals, or I can combine the radicals together into one radical. So here, I'm just combining those two radicals into one single radical and multiplying, and that gives me a nice perfect square. Or look at this one. The square root of 3x times 4 times the square root of x. So all these things underneath the radical I'll combine under one radical. And x times x is x squared, so that's why now I have x squared underneath the radical. And now think about this. I have 4, I have the square root of 3, and I have the square root of x squared, and that's a perfect square. The square root of x squared is x. So I have 4x times the square root of 3. Okay? Or in this next problem, we have the square root of 7xy to the second times 3 square root of x. So they're going to take these two radicals and combine all these variables and numbers underneath the radical underneath one radical. So you can see they combine them together, 7xy squared times x, and then the 3 is still out front. They combine the x's. We're multiplying. So we have 7x squared y squared under the radical. Now they'll take the radical and break this up into separate factors. I have the 3 in front. I have radical 7. I have radical x squared and radical y squared. And these can simplify because the square root of x squared is x. The square root of y squared is y. And then this is 3xy radical 7. I just simplified it. It's always important when you write a product involving a radical to write the radical last. So you notice in the answers here, let me highlight these. You notice in this answer, they wrote the radical at the end of the problem. You notice in this answer, they wrote the radical at the end of the problem. You always want to write the radical last at the end of the problem. Okay? There's another property that we need to know. This will help us with the fractional aspects that we had talked about on the first slide. You know, we can't have any fractions in a radicand or no radicals in the denominator of a fraction. This quotient property will help us with that. The square root of a quotient equals the quotient of the square roots of the numerator and denominator. And that might sound terribly complicated. It's not. Here's all it's saying. If you have a radical and a fraction inside the radical, you can break this up into two separate radicals. Like the square root of 16/25, I could rewrite that as the square root of 16 in the numerator and the square root of 25 in the denominator, and that would just be 4/5. So that's all this is saying. I can take a radical, a fraction that's inside of a radical, and break it into separate radicals, one in the numerator, one in the denominator. Let's see that at work in these next examples. Use the quotient property of radicals. So here I have a fraction inside of a radical. So I can break this into the square root of 13 over the square root of 100, and now think, what is the square root of 100? Well, it's 10. There's my simplified radical, square root of 13 over 10. Now remember the rules for simplifying a radical. You can have no fractions inside of a radical. So let's look. If I go back, You see here, I got rid of the fraction there's no fraction in a radical in my final answer. And then here's the other thing, going back. I cannot have a radical in the denominator. Well, do you notice I got rid of the radical in the denominator? I have a whole amount, 10. Now, it's okay for me to have a radical in my numerator in a simplified expression. I never want to keep a radical in the denominator. Here's another one. You see, one of the rules are being broken here. We cannot have a fraction inside of a radical. So let's start off by writing this as separate radicals. And then the square root of 7, there's nothing I can do with that, but look at here. The square root of x squared is x. Well, I just eliminated that radical in my denominator. So all my rules are followed. I do not have any perfect squares under a radical. That was rule 1. I don't have a fraction inside of a radical anymore. That was rule 2. And I don't have any radicals in my denominator. That's rule 3. That's why this is simplified. Why don't you pause the video real quick and try these? So for the first one here, I decided to combine these underneath one radical. So I have 2x cubed times x under the radical. And x cubed times x to the first is x to the fourth. So now I have 2x to the fourth underneath my radical. And then I broke this up into two separate factors. I have radical 2 times radical x to the fourth. That's a perfect square. The square root of x to the fourth is x squared. So the x squared is now out of the radical, and I still have the square root of 2 in the radical. So there's my simplified response for the first one. For the second problem, I can't have this fraction underneath the radicals, so I broke this into separate radicals, and then the square root of 1, that's easy, it's 1, and the square root of y squared is y. There is my simplified answer. All my rules are followed. I don't have any radicals left, there's no fraction inside of a radical, and I don't have a radical in the denominator. Okay? Rationalizing the denominator. The example below shows how to eliminate a radical from the denominator of a radical expression by multiplying the expression by an appropriate form of 1. I'll explain that in a minute. The process of eliminating a radical from an expression's denominator is called rationalizing the denominator. So this is the process that you use to get rid of radicals in the denominator. So look at A. We have 5 over the square root of 7. Now we have an issue here. The square root of 7 isn't a perfect square. So here's what you can do. You can multiply the numerator and the denominator by the square root of 7. So let me color code so you can follow that. Here's the original problem, and they rewrote it again, and then you notice in yellow they are multiplying the numerator and denominator by both the square root of 7, which is the equivalent of 1. Something over itself is 1. Now, in the denominator, let me circle this. If you combine those together, you'd get the square root of 49. And in the numerator, you'd have 5 square root 7. But now think, what is the square root of 49? It's just plain 7. You just simplified this. Let's make sure all the rules were followed. Rule number 1, we can't have a perfect square underneath the radical. We don't. Rule number 2, you cannot have a fraction inside of a radical. We don't have a fraction inside of a radical. And rule number 3, we cannot have a radical in the denominator, and we don't. Same thing for B. Let me color code again, so I think it's easier to follow when I do that. So here's the original problem. None of these are perfect squares. So I'll rewrite the problem again, and I'm going to multiply by the square root of 3b in the numerator and denominator. Now, the reason we picked that is look at the denominator. That's what we had. Okay? Now, let's go to the numerator. If you combine these together, underneath the radical, 2 and 3 is 6. You have radical 6b in the numerator. In the denominator, when you combine these, you get radical 3 times 3 is 9, and b times b is b squared. And now I can simplify what I'm going to highlight here in orange. I can simplify that because I have the square root of 9 and the square root of b squared, and the square root of 9 is 3, and the square root of b squared is b. There's my simplified answer, Right here, it's the square root of 6b over 3b, and all three rules are followed. I have no perfect squares inside my radical. I have no fraction inside of a radical, and I do not have a radical in the denominator. Okay? Let's keep going. Sums and differences. You can use the distributive property to simplify sums and differences of radical expressions when expressions have the same radicand. Another way of saying that, I think this is more confusing, that's just my opinion. I think this is an easier way to say it. Another way of thinking about what this says is the following. You can only add or subtract like radicals. Like you have like terms all school year. You know you can only add or subtract like terms. It's the same here. Like look at this problem right here. Do you notice I have this 4 square root of 10 and minus 9 square root of 10. I can subtract these because they have like radicals square root of 10. So 4 square root of 10 minus 9 square root of 10 would be negative 5 square root of 10, plus I have radical 13. I cannot add these together because these are not alike. So this is the best I can do to simplify my problem. I have negative 5 radical 10 plus radical 13. Now, the square root of 10, there's no perfect square. 4 and 9 don't divide evenly into 10 or 13, so I can't simplify those radicals anymore. Or here's another one. 5 radical 3 plus radical 48. So I have 5 radical 3. I broke 48 up into 16 times 3 because 16 is a perfect square. I can simplify that. So now I have 5 radical 3 plus radical 16 times radical 3. The square root of 16 is 4. So now I have 5 radical 3 plus 4 radical 3. Do you notice how those are like radicals? They're both radical 3. 5 plus 4 is 9. I have 9 radical 3 for my simplified expression. Why don't you pause the video and try those 3? Okay, and I'm back. So the first problem, I can't have radical 3 in the denominator, and that's not a perfect square. So if I quickly multiply the numerator and denominator by radical 3, I have 1 times radical 3, which is radical 3 in the numerator, and then radical 3 times radical 3 is radical 9, and isn't radical 9 3? So there's my simplified expression. For number 4, I can't get rid of radical x. I can't keep it in the denominator, so multiply the numerator and denominator by radical x, and 1 times radical x is radical x, and now in the denominator, I would end up with these two multiplying into radical x squared, and that just gives me x. So x, square root of x over x is the answer. For this one, I can't keep radical 2x in the denominator, and there's no perfect squares in there, so multiply the numerator and denominator by radical 2x. In the numerator, I have 3 times radical 2x. In the denominator, when I multiply those, I get radical 4x squared, because 2 and 2 is 4, x and x is x squared. And you notice, that's a perfect square, 2 and x. So 3 radical 2x over 2x is my simplified radical. And then finally, in this last one, 2 radical 7 plus, I have 3 radical 63, and I notice, wait a minute, 9 goes into 63, so I broke this into 3 times radical 9 times radical 7, and then radical 9 is 3, so now I have 2 radical 7 plus 3 times radical 7, and 3 times 3 is 9, so that's where I'm getting the 9 radical 7 from, and you notice how these are like radicals? I can add those, that's 11 radical 7. Okay, you might have to distribute when you multiply radicals. Okay, like here, I'm doing this times this and this times that. So I get 4 radical 5 minus radical 5 times radical 20, and those I can combine into radical 100, and the square root of 100 is 10, and then there's no like radicals. I just simplify it. And you'll notice over here, they're just double distributing. They're taking radical 7 times itself, which is here, radical 7 times 3 radical 2, which is here, radical 2 times radical 7, and then radical 2 times negative 3 radical 2. So the square root of 7 squared, those cancel, I get 7. And here I'm getting negative 3 times radical 7 and radical 2 combined together, which is radical 3, radical 14. And then here I'm getting radical 14. And then here, radical 2 and radical 2 is radical 2 squared, and then I have the negative 3 in front, and the square and square root cancel. That's 3 times 2 is 6. So let's combine our like radicals. 7 minus 6 is 1. And negative 3 radical 14 plus 1 radical 14 would be negative 2 radical 14, and there's my simplified radical. Okay? And I think that's about as far as I'm going to go on the video. In these word problems, these would be calculator questions where they're basically just having you simplify, like they showed you how to simplify a formula here. And this is just a review of what we covered. And then you're going to use your calculators to substitute a number into the formula to figure out the answer. So I'm going to just kind of let you look at that on your own. So I'll stop the video here. If you have questions about simplifying radicals, make sure you ask her in class.